Hi everyone. Welcome to Lecture 2. We're going to be discussing data models and map design today. Our overview here is that we're going to look at data models, of course. We'll discuss attribute tables and their utility. We'll talk about some relational database management systems, or rasters, and their limitations. We'll also touch again on vector files, and then we'll go through what scale, distortion, and projection mean to us. So starting off, we're going to talk about shapefiles. Now, shapefiles here are simple and non-topological formats that allow us to have or store geometric information, geographic information, through attribute tables and geographic feature classes. These features can be in the form of points, lines, or polygons. So you'll see here in this figure that we have a folder labeled data. Within that, we have another folder or subfolder called USA shapefiles. And in that folder, we have our tables as well as our pure shapefiles. So you'll see here in tables, we have a few different formats of folder or file type. We have a text file and a database file. And then also within that folder, we have our shapefiles for city, counties, roads, and states. And you can tell by those icons next to each one of those shapefiles, you can see that some of them are point shapefiles, some of them are line shapefiles, and some are polygon shapefiles. What this means for you is that when you're working in ArcGIS Pro and you either import or pull in one of these shapefiles, for cities, you're only going to have points on your map. That's the type of geographic information you'll have there. For counties and states, you'll have polygons, and for roads, you'll have lines. So editing with your shapefiles, you can edit them directly in ArcGIS Desktop or in our case, ArcGIS Pro. In order to take advantage of advanced editing, such as topology, you'll have to import that shapefile into the Geo database as a feature class. One theme that you'll find kind of common is the utilization of the word feature class and shapefile as if they are the same. For the sake of our course, they are essentially the same thing. So you'll hear me discuss shapefile, you'll hear me discuss feature class. Think of these both as the same thing. Essentially, a feature class is just what a shapefile becomes when you actually view it and bring it into ArcGIS. So to talk about topological models, these are essentially models that give us vector data on topology, such as the name implies. Now, you're going to see here, we have this comment about unlike spaghetti models. I'm not talking to you guys about spaghetti models in this lecture anymore, so ignore that portion. Topological models allow for more advanced analytical techniques to be performed in ArcGIS, and it makes it far easier to do so. This is done by explicitly using adjacency information in a data structure where data is input. So each line is called a link, and each line has a specific identification number. Essentially, each line segment is going to start and end whether it contracts or intersects with another line, or if there's a change in direction. So every line is going to have two sets of numbers. You're going to have a pair of coordinates as well as an associated node number. We then talk about map models, or MAP models. This is one of the many ways that computers store and reference information in a grid cell value, as well as their attributes, the map names, and the legends. So in a map model, each variable has its own code, and that is referenced by recall by the machine. Essentially, what this is that your computer understands what each code for something in that model means, and you are very easily able to pull, extract, and utilize the information within that model or that code. This lets you really easily manipulate attribute values within grid cells and allows you to utilize many-to-one relationships. This will make sense to you a bit more as this lecture and more lectures go on. Quantizing versus indicating geographic space. So these are very big words with very basic meanings. This essentially is the conversation between what a raster and a vector are. The moral of the story here is that everything in GIS can be simplified and related to other concepts. So remember this and focus on the big picture, not only in this lecture, but throughout the lectures in this asynchronous course. A raster specifically uses a full grid cell, and it does not provide a precise location. So remember the star being in the middle of the grid cell from your last lecture, whereas a vector is a very precise location. Now, I want you to ignore the last two bullet points on here, the quad trees and everything. Essentially, when you think of a raster, think of the raster encompassing an entire grid cell, whatever value might be in the center where a vector would be. A raster encompasses that entire value within the cell. Moving over to dimensions and resolution. We understand dimensions as in 0D, 1D, 2D. These are also how we refer to raster dimensions. And of course, we have 3D as a dimension, but that is not something that I go through in this course. Whether you're taking my summer course or whether you take one of my spring or fall courses, we don't focus on 3D modeling in Introduction to GIS. So in our case, what's relevant to us is that the 0 dimension will refer to points for us. They don't have a dimension. A point is just a dot on a map. A line will have 1 dimension, and it's a flat line, one-dimensional. And an area or a polygon can have 2 dimensions. In terms of resolution, think the larger that the grid cell is, the more land area is going to be contained in that grid cell. So the more land area, the coarser the resolution. Essentially, a large grid cell has a coarse resolution where a small grid cell should have a finer resolution. This doesn't seem pretty inherent at first. You would think that a large grid cell would have high resolution, a small grid cell will have coarse resolution, but if that's how you think of it, just write this down and refer back to it. When we talk about resolution, large resolution, small resolution, what's not, what we're really saying is that a large grid cell is going to have more coarse or zoomed out information, and a small grid cell is likely going to have more specific and fine resolution. So now we can discuss vectors in terms of one-to-one. There are going to be many types of relationships when it comes to your data, your maps, and your attribute tables. In this case, we're speaking again of a one-to-one relationship in a vector file. So you'll see in this figure, we have this square, or this map per se, where we have A, B, C, D, and E as different polygons on this map. You see that these arrows going back and forth between the map and the table are showing you that for polygon A, there's only one row in the table that refers to polygon A. It has an ID, it has a class, and it has an area. There is only one row per polygon, which means that for the map, there is a one-to-one relationship between what is on the map and what is in the attribute table. And you see that this continues to be true for all of the other polygons B, C, D, and E within this map. Now moving over to a raster file, which again, a raster value encompasses the entirety of a cell. So you'll see here a cell or a square essentially on this where it says A takes up the entirety of that cell. The value of A takes up the entirety of that cell. You can very quickly realize by just looking at the map and looking at the table right there, a one-to-one relationship for a raster doesn't often make sense to use. It really wastes a lot of space. It takes up a lot of memory for your system to see that, okay, here's all of these different cells that have A. Let's list out all of these ID orgs of A, and then give each cell its own ID, when each of those IDs, classes, and areas are exactly the same. Because again, a raster, when we talk about rasters, we talk about each cell in a raster having an overall value. If there's 15 cells in a raster, and they all have the same overall value, a one-to-one relationship doesn't make sense. More so, we like to talk about rasters and utilize rasters for many-to-one relationships. You see here, instead of using A's and B's and such, instead of using letters, we're using numbers. But we have multiple cells that have the value 10, multiple cells with the value 11, and so on. So there's many raster cells that all relate to one row or one line in your attribute table. This is a lot more clear. This is a lot more straightforward. And in terms of you as a user with the interface, it is a lot easier to use. So now we have basic building blocks for assembling GIS data layers, such as points, lines, and polygons. But our task as a user with ArcGIS is to decide how to use those components to represent entities we find in the real world. So for example, if you have a lakes data layer, what is it supposed to look like? So essentially when we talk about an entity is supposed to be a representation of something that's in real life. So a lake can be potentially a municipal water source. It could be a recreation area, a flood control sink, or a wildlife habitat. A lake itself can be multiple things. Typically, we're going to store different object types, even from the same entity in different layers. So bringing it back to lakes and how we kind of represent this as an entity on a map, you see that we have at the bottom, one of these bottom images here, we have an example of a lake boundary and a lake center point. When we look at a lake boundary, we choose to symbolize this or represent it as a polygon. We're looking at the entirety of the boundary of that body of water. But maybe we want to show it as where the center point of that lake is instead. Maybe we're not interested in what the actual boundaries are. Maybe we're just interested in there's a lake here, 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 and here, and we just need to know the amount of lakes within a certain area. Maybe we just need to get a count, per se. Whereas when we use a polygon for lake boundaries, maybe we're trying to understand the difference between sizes of lakes. So again, typically we're going to represent entities as one of our four types of objects: a point, a line, a polygon, and sometimes 3D objects, which in this course, again, we don't look at. So what could we use a point layer for? How about a line layer or a polygon? The image I have on the screen for you here gives you an example of how you can use points, lines, and polygons to symbolize or represent the same entity in a variety of ways. You can take these buildings that are in the left image and you can represent them by just center points. You can put out the lines just to give it an idea of what the boundaries of these buildings are. Or you can put a polygon to get an idea of the area that each one of these residencies or buildings takes up. So talking now about spatial resolution and extent. For vector data, storage required is not directly dependent on the extent, but rather the number of features and their complexity. You'll see here in this first green box that we have, essentially space, or the resolution of space, is equal to a function of the number of features and complexity. Whereas for a raster, that function is going to be based on resolution and extent. Raster data storage is required and determined directly by a function of that resolution and extent. That's what gives us the number of pixels that we need, whether we have a larger or coarser cell or whether we have a finer and smaller cell. Your takeaway here, you don't need to memorize at any point throughout this course any of the functions or equations that I give you. What I'd like you to take away from this is that vectors and rasters fundamentally store information differently, and they are based off of different pieces of information. This is not something that you won't directly create vectors or rasters throughout this course. What you'll do instead is you'll decide, especially for your final projects, whether or not a vector dataset is the type of dataset that you need, or whether a raster dataset is the type of dataset you need. I'll try not to get ahead of myself here. As we kind of go on in our lectures and this lecture, you'll understand a bit better when you may choose one or the other. But essentially, the way that data is stored and it's represented even from vectors and rasters is different. Going over to talk about coordinates now. Coordinates used in vectors are floating point numbers, and they typically require at least 32 bits or 4 bytes of data. In a raster, the coordinates are implicit. So instead, they take no space. However, you have to provide one attribute value per cell, because remember, a cell has one overall value for the entirety of that cell. You don't need to focus on the bits or the bytes in this. You just need to understand that in terms of coordinates, your vector is going to be far more specific. It is going to actually have these coordinate points. Whereas in a raster, you're going to have an overall point for each cell, and that's it. So here, data 3 points, I actually think I might skip through. Yeah, I'm going to skip through these few slides. I don't really feel like you need to know this too much. You're welcome to pause and read through these, but these examples won't really be too relevant for you in the course. I typically go through this a bit more in our semester when we have more time. Here, I want to show you an example of the same type of data represented as a raster and as a vector. On the left-hand side, we have a raster file, and on the right-hand side, we have that vector file. You can represent the same things across two files. There's not always a right and a wrong in terms of whether you choose a raster or a vector. More so, you just need to know what it is that you are seeking out, what it is that you want to do with your map. So you see here, if we focus on the vector file, you see that this is giving us an idea of topography. We're probably getting an idea of elevations. This is a very generalized map, but you can kind of understand here that you can see where you may have a higher elevation versus a lower elevation. Maybe you would use a vector in this case to understand the difference in elevation between each one of these rings or each one of these topography layers. Whereas with a raster, we're looking at the same data, but it's a lot harder for us to understand the differences in elevation in this raster. More so, it's easy now for us to see where those little tributaries of that river come off. It's easier for us to see where the river itself is in relation to the masses of land. So the raster is giving us more of I like to kind of think of it as like a satellite view. Typically, you'll see these raster files in terms of satellite data, whereas a vector is really giving us that hard line map. So choosing between a raster and a vector, you need to ask yourself a few questions. First, you need to think about how dense the collection of measurements is that you have. Do you have a lot of measurements, or do you have something that's more manageable, right? It's the difference between 100 measurements versus a million measurements. Are they regularly distributed in a grid? Yes or no? If they are, maybe you go towards a raster. If they aren't, maybe you go towards a vector. Are they continuous or are they categorical? This will also give you an idea of whether or not you want to go for raster or vector. Do you have to calculate any statistics based on surrounding areas? And do you need to represent lines? Those last two questions will give you a pretty good idea of whether or not you need to do a vector or a raster data type. If you have to represent lines and you have to calculate statistics, you're probably better off utilizing a vector data set. But if you don't need to do those two things and you have a million data points, maybe you choose to go with the raster instead. So now we come over to talk about attribute tables. And essentially what an attribute table is it's just a table of all the attributes or all of the qualities of a layer. So you'll see here, we have this table that's representing states. And you'll see that we have our first column called object ID underscore one, our next column called shape, and then we have ST, USPS, name, object ID, and so on. A column is going to refer to a field. You'll hear these interchangeable between me, the tutorial, and just general jargon. A column is a field. A row is a row. So there's no really change there. A row is a line, and you'll see that they're always going to be labeled by their object ID or some form of ID, numbered 1 through however many you have. In this case, we have 52 objects in our attribute table, which we can see by looking at the bottom of this table. So this would run 1 through 52. You'll see again that each one of these columns has different information in it. And there's a big difference that we don't go into very much in introductory GIS, but I do like to point out to my students. You'll see in these first two fields, or these first two columns, that there's an asterisk after that field name. For object ID underscore one and for shape, there's an asterisk. What this tells you is that these columns or fields cannot be modified. You can go ahead and click into this field that's called name, and you could change the name of Alabama to AL if you wanted to abbreviate it. You could change it to lowercase Alabama instead of uppercase. You can make it all caps. Essentially, you can play with the name and the data within that cell. However, if you go over to the object ID or the shape field, you cannot play with those. So this row one or line one is always going to be called line one by your system. The reason that this occurs is because of something called primary keys in GIS. Again, you all don't learn this, so I try not to confuse you about it, but I like to bring it to your attention so that as you work through tutorials and as you work through assignments, you can recognize where there is a field or column that you're not able to edit. You leave those ones alone because there's essentially a relation between that field and something else going on in GIS or something else in the attribute. It's not for you as a user to understand at this point. It is just for you to recognize and understand that you cannot edit those cells within those fields. You can edit cells in other fields that do not have an asterisk after the name. So, of course, as we just mentioned, attribute data is often stored in a table. You'll see here that for each of these fields, we have a different type of information that's stored, and they're all related to based on their row or their line. So this row here, this top row, has an ID number of 27. The area of what we can assume now is a polygon because it has an area is 39.2. We don't know the units yet, right? The perimeter is 55.4. It's classified as class A and it has a code that is 11Z. You'll see that that second row has different information within it. Storing it in a table view is very user-friendly and it allows us to very quickly see in ID number 75 what is the area, perimeter, class, and what's not. Also in your attribute tables, you can click and highlight things from the attribute table onto your map to see what that object is that it's referring to. Whether it's a point, a line, or a polygon, you can right click and do flash as an option, and it'll flash on your map whatever that row refers to. So here again, your attribute, which is also an item, a field, or a column, and then your record or your row or tuple. Nobody calls these tuples anymore. You're going to hear of it as a line, a row, maybe as a record. So how do we relate an attribute table containing non-spatial features? How do we refer to it or how do we relate this? We can utilize one-to-one relationships, which is the most common thing for a vector, as we saw a few slides back. We can use a one-to-many relationship, or we can use a many-to-one relationship. There's three types of relationships here, but there's two that are mostly distinct to their database type or their data type. One-to-one is most common for your vectors, and many-to-one is most common for your rasters. If this doesn't make sense to you, ignoring the one-to-many at this moment, go back in this video or go back a few slides and look at the example that we have of our map versus the attribute table again, and it'll make a bit more sense. Now, we've talked about the idea of compaction a bit in 2.1, or I don't know if I have it as 2.1, 2.2 for you right now, but essentially when we kind of talk about data management before lecture 1 even, and how to organize your files, we talk about what a zip file is. A zip file is your best friend, and it is my best friend, and anybody who works with any sort of large data sets loves these and has to use them. So GIS is going to create many small files that all have to be together, packaged together, and loaded together in the same exact folder for your map to properly load. If you do not do this properly, for example, if you save your map that you've been working on in a folder outside of its source or outside of its source data, you are most likely not going to be able to send over the information on the map that you see and have the person you sent it to see that same information. I mentioned this in some of your slides again earlier on before lecture 1, where if you are to save information outside of its essentially like parent folder, if you save an APRX file out of there, if you delete certain folders or files outside of the home folder, when you send it over to somebody else, such as myself and your grader, when we open it and decompress it, we're going to see these red exclamation points next to certain data layers that say data link broken. This is because you have essentially corrupted the file. You have not properly compacted it or properly zipped it. So the long story short here, instead of having a whole other lecture on this, is that the compression or compaction and the decompression of a zip file is a very proper and standard practice in utilizing any sort of GIS. So please make sure that you practice this. Please make sure that you check your files before you submit them to us. The best way to go about this is to open remote apps, whether you use remote apps for utilizing GIS or not. Open remote apps and have it emailed to yourself, that compressed folder that you're going to upload to us. Access your email and remote apps, download the zipped folder, decompress it, and try to open your map. If everything shows up perfectly, you're probably great. If you open it and you see those red data, those red exclamation points, and those data links broken, you know that you need to go back to the actual file folder that you were working in, and you need to go ahead and check to see what might be going on there. If you struggle with this, I highly recommend you post this in Piazza and you try to get on top of these types of issues as fast as possible. So coming back to the point of this lecture, mapping. So making maps is a core, and I would say the core function of GIS. A good map is going to be based on scientific principles, but great maps also have very strong artistic components to them. Now, there is such thing as distortion within our maps, and this is something that not only refers to aesthetics, but it also refers to our scientific principles. So all maps have three basic attributes: a scale, a projection, and a symbolization. Each element can source distribution. As a group, they describe the essence of what a map's possibilities and limitations are. This is from a quote from Mark Monomere of How to Lie with Maps, which I highly recommend you look at if you're ever bored one day and looking for something good to read. What this means for us is that every attribute that a map has, or every piece that a map has for us, has an ability to bring distortion to our map. This means less accuracy, the potential for improper representation, and confusion for the person looking at the map. To fix this, we make maps that have intentional scales, intentional projections, and intentional symbolization, so we hedge the inevitable distortion and we can lessen it. You cannot completely remove distortion, but you can lessen it to a point where it does not get in the way of what you're trying to represent. So maps aren't just lines. They contain many helpful textual and graphical features. You can see this is an older map. This is a scanning of a map from the Virginia, North Carolina Back Bay. You'll see that there's a few different things going on here. You see we've kind of zoomed into the scale. We have that approximate mean declination, 1930, that's all the way very small towards the bottom of that map. And then we also have these coordinate points to tell you at a certain boundary what the coordinate points are. So, of course, this is an older map. You're not going to be scanning in or creating these. Maybe you will for your final project if you please. But every piece of a map is intentional. Going over to the scale, if we didn't scale down sizes or if we didn't scale down maps, essentially everything would be a real life representation, size wise, of what we're trying to show. And if we wanted a map of the Earth, the map of the Earth would be as big as the Earth. If we wanted a map of Virginia, the map of Virginia would be as big as Virginia. So, of course, we have to scale things down. So sometimes we use scales for like 1 to 10,000, 1 to 500 to represent large areas into smaller images. Something you'll hear often is people saying a large scale map when they mean a large area map. A large area is going to be small scale because you have to scale it down to represent something large. This is just semantics, but something to keep in mind as you learn through this course. Now we talk about generalization in maps, right? We have to generalize features because, again, if we didn't generalize them, there's so much detail and so much difference in sizing that happens that we would really be doing ourselves a disservice. Essentially, we want to generalize, for example, a lake. We don't need to have every nook and cranny of a lake drawn out or digitized in our map. What we need is some sort of a blob that represents generally what the shape of that map is. Of course, this is if we're looking at a larger area projection or a larger area map. So just like we have generalizations, we kind of simplify entities onto a map. We also have exaggerations, such as the map of Virginia in its highway system that you see at the bottom left. Here, these interstate highways are exaggerated because we're trying to show whoever is viewing our map that this is what we're trying to talk about. This is the point of the map to show you where those interstate highways exist, what cities and counties that they cross through. We're not really trying to tell them that, like, oh, hey, look how cool the shape of Virginia is. Or, oh, hey, here's the topography of Virginia. Or, oh, hey, like, here's where Richmond is in relation to Virginia Beach and Chesapeake. That information is on the map, except for the topology, but that information is on the map. That's just not what our reader is going to be interested in. We want to talk about where the interstate highways exist and where they intersect. So we do a bright red line, we do a bolded line, we make the interstate highways larger, those lines representing them larger than the other lines on the map. So it is very clear as soon as you look at it that, oh, this is a map of the interstate highways of this state. Now, of course, different maps are made to relay different information. So where you may generalize certain information on one map, you may have to exaggerate it on another. So these maps are past submissions from years back, different final projects that students have submitted. On the left-hand side, you can see that we're just talking about UVA central ground structures. You can see whether or not the structure is historic or not, and it's color-coded based on the year that it was built. Now, on the right-hand side, we see that we've zoomed in ever so slightly. So you'll see the rotunda is right here on our left-hand map, and this is the lawn. Here we're zoomed in a little bit. And what we're interested in is very different. What we're interested in here is streaking the lawn at UVA. We're interested in your starting points, your turnaround points, and all the points in between that you need to go to properly streak the lawn. Um, I'll leave that as is. This is not me recommending that you do that. This is not me commenting on whether or not you do that. It's just a fun map that we show throughout all of our semesters because it's a good map. So there is something that John Porter, who typically teaches this course at UVA, likes to call the 6 W's of maps. Don't get mad at me for the last one because it doesn't start with W, but the first W is why. So what is the purpose of this map? Why are you making this map in the first place? Then we ask who. So who is the audience that the map is intended for? Then what is the important information that we're trying to communicate? Where is the geographic area of interest that we're trying to show our why, who, and what? And then when. So when the events or the ground condition occurred, also the time periods for which that data is available. The last one we have is how. So how is very important to us. Given data constraints just in general life, whether or not data might be behind a paywall, whether or not data even exists in the first place, are we able to create this map? So there's always going to be the why you're making the map, who you're making it for, what you're trying to relay, where the information is or where the area is that you're trying to relay, and then when you can get the data from. But the overall question with all of these, with these past 5 questions is, are you able to get the data? Are you able to access that data, whether it's your time, whether it's your money, to be able to create a map in the first place? So these are things to think about as, again, we get closer to final projects throughout this course. When you start thinking about the ideas you have for your projects and even personal projects that you use for GIS or use GIS for, ask yourself these things and ask them in this order. What are you trying to make? Like why is the map being made in the first place? Who is it that's going to be looking at this map? What's the information that you have to communicate? Where is the information located in real time, in real space? Is it the United States? Is it North America? Is it the Middle East? Is it Australia? When can you access data or when can you get data to represent this information? Are you only able to access data from the 1920s? Do you want information from the 1800s? Do you want information from 2026? That's going to be a big factor. And then finally, how you're going to access this data, how you're going to eventually make this map based on whatever is available or whatever is not available to you. So we come over now to symbology. Our maps are representing, again, entities, and the way that they do this is through symbols. Symbology is a mechanism for the mapmaker to convey to you what is important to the viewer, and that's by drawing your attention to certain objects. Think back a few slides to the map of Virginia, the interstate highway system. We are drawing our viewers' attention to those interstate highways through the way that we symbolize those highways, bolding the lines and coloring the lines, for example. So symbology is going to include your map type, your lines, your shading, your colors, and any text or annotations that are on your map. Here's an example that you can see now of different symbology across maps. You see over here on the left, this larger map is a choropleth map or a heat map. You see that as we have a higher population per square mile by state, the shading of these states gets deeper. It becomes a deeper color of purple. You'll see here we have a feature map. So this feature map is essentially telling us, well, what are all of these locations? This is, I think, the Eastern Shore that we're showing over here. What are all these locations? Over here we have Wallops Island. Down here at the bottom we have Smith Island. We have Fisherman's Island. So what we're trying to get across in the feature map is what the actual thing is that we're looking at across our geographic space. We have a contour map over here of Yosemite that shows us the difference in elevation, the difference in basically our topography as we move through Yosemite. Also, contour maps are used in any sort of meteorology when we talk about high pressure, low pressure systems. You might recognize this if you've taken a meteorology course in the past, or even if you just like to browse NOAA or observe your weather through some more complex systems, for lack of better words. But contour maps essentially are trying to tell you within a certain space, within a certain polygon that we're representing here, there's a difference between this one, the one that's inside of it, and the one that's inside of that. Typically, the more that we move inwards or the closer lines are on contour maps, it means that we're very quickly increasing elevation or value of some sense. For the weather maps, we're going to be very quickly increasing our pressure system, for example. And then down here at the bottom left-hand side, you'll see just a variety of different types of symbolizations on maps. You see your top, you have your dot map. Below it, you have graduated symbols. Below that, you have flow. You also have, again, a choropleth map at the top right of it, a pie chart map, and an isarithmic map, which is a contour map. If you hear the word isarithmic, you really don't need to worry about that because people can just use layman's terms and say contour maps. Goal here is for you to just see the idea of all the different ways you can symbolize information and where you might use a certain type of symbology for what you're trying to get across to your viewer versus another type of map or symbology for other things you're trying to get across to your viewer. So the elements of symbology, individual elements can be combined to create a very large number of combinations of symbols. Easy example here is that you can see that we have these different types of reds. We also have these different types of textures, whether or not we have just a few dots on our cell, whether or not we have a lot of dots on our cell. We can also change the shape of our symbols. We can change whether or not they have a bit of like a raised or 3D effect. We can also see if there's different patterns and sizes. So there's a variety, there's many, 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 many ways you can symbolize things. You will never be short of ways to symbolize something. So something we typically like to play with in this class is a figure here that actually is asking, which of these maps do you think has the highest shrub density? From the left-hand side, we're moving from 1962 all the way down, from the left-hand side starting at 1962 all the way to the right of 2005. And it's pretty easy or pretty intuitive to say that in 2005, we have the highest shrub density. But why is it that you think that? The obvious answer here is that all of these black dots, there's so many more of these black dots in the 2005 map versus the 1962 map. And it's the only thing that's changed. The only change that we very clearly see here is the progression of those maps. Now, this is because we used good symbology. Another thing that you'll notice if you take a deeper or closer look is the shape of this polygon or this landmass has also changed. There's some coastal erosion going on here. So where we kind of have a lot more of these grooves and divots and we have this more sharp northern spike of this landmass, you can see that it rounds out over the time of this study. You may not notice that at first because this was good map making. The person who created these maps did not want you to look at these maps and be like, oh, well, the shape has changed of the overall landmass. What they wanted you to see is that there's a difference in those dots, which represent shrubs in our case, between 1962 to 2005. So the symbology here was proper for the goal. Now here, we like to ask, well, can you easily tell within these four maps what is land and what is water? If you start out looking at the top left corner, which is labeled A, now you may know what Italy looks like, but if you weren't given any of these other three maps and you were to just take a look at map A, it's very difficult for you to understand that that's Italy. And it's also very difficult, even if you know that, to know what is land and what is water, unless you have a perfect image in your head of the boot that Italy looks like. The reason is that in A, there's no perceptible differentiation between the land and the water. Now, B and C try to do a better job of just shading the land and the water. But in B and C, the land-water differentiation is only obvious if you're familiar with the area or if you're familiar with Italy itself. Figure D at the bottom right-hand side is a perfect way to represent this information because it has a differentiation between the land and the water. The colors or shading is different. And then we also are labeling each of those countries, each of those land masses. This way, we're able to say, oh, this is water, which is in the more like gray, black shading in the back, because this is Italy, this is Yugoslavia, this is Hungary, and we know that these are land masses. So something that you may not think of when you look at a map typically. Something that you might think is like a duh type of moment is a very intentional choice by the person creating the map. And you are now the person that is creating the map. A very good practice is to check over and look through color combinations. This isn't a slide that I'll harp on. You can always come back and pause this. You can also do a bit of a deeper dive online by looking at what color configurations look best with one another. So making a black and white map first is a good idea. Then adding on colors, looking at what you want to be starkly different. Maybe you put very different colors in. Looking at what you want to show a gradient with. Maybe you do multiple shades of red to show higher to lower levels, reds to blues to show low temperatures or low levels versus high temperatures, high levels. Color combinations are going to be very unique to what it is that you're making your map for. So this is not something I go too deep in, but it is something that you need to focus on and think about with every single map you make. So just keep this in the back of your head when it comes to your aesthetics and your symbology. Coming over to color gradients again. So here's an example of the same exact information being portrayed in two different color scales. This is showing the 2004 election. The upper hand map is showing you these very fruity colors. By that, it means like it literally looks like a bowl of cereal, it looks like a bowl of fruity pebbles. You have reds and oranges and blues and greens. And although it's showing us what is meant to be an intentional differentiation between large, medium, and small wins for each of our candidates, when you look at that map, it is very difficult to tell what's going on. Mostly what we're seeing is this dark blue color. That's really what sticks out the most to you, and then a few of these dark red colors. But it's very difficult for you to say, if you were just to look at that upper map, what countries have the highest rates, or sorry, what counties have the highest rates of votes for each party, and which ones have the lowest. A much better idea, if we're looking at two candidates in this case, Bush and Kerry, is to just use a gradient that is two colors and a difference of shading between those colors. So we have red and blue as our primary colors in our bottom map. And then we have some shades of red and we have some shades of blue. It's very intuitive that a deeper red means more of something, and a lighter red is going to be less of something. So looking at that map on the bottom, you can see that, yeah, overall, there were very many more votes for Bush than there were for Kerry. If we look at the map on the top, what's very clear to us is that there were a lot of medium Bush wins. A lot of counties had a medium-sized win for that candidate. So it's, again, important for you to be deliberate and intentional with the gradients and the colors that you use. A good map is going to combine multiple things. It's going to combine very specific choices based on the scale that you choose, what generalizations you choose to make versus not, what symbolizations you choose to use, and the actual layout of the map itself. Essentially, a good map is going to have a very clear purpose, and you can sacrifice accuracy in order to achieve that. What that means is that if you have, again, a lake, for example, instead of that lake being a perfect small representation of the real life lake with every little groove, every little divot and such, maybe you just make it a blob that is the general shape. As long as your map is very clearly getting across its purpose that this is a lake and this lake is, let's say that we're comparing distances or sizes of lakes. This lake is this large and it's this far away from something. This lake is this large and it's this far away from something. As long as the purpose is clear, your reader does not, or your viewer does not need to know every single detail about that entity it's representing. So of course, there's issues in any sort of symbolization. This is going to be another example here looking at voting in terms of whether we vote red or blue. Now, this is a very generalized map because we only have two colors. Unlike the map we had a few slides back where we had shades of red and shades of blue, this map is essentially just red or blue. What we miss from this map is, let's look at Texas. Texas is red. That was a Republican voting state. But did everybody in that state vote red? And are there the same number of voters in each state? For this map and for its purpose, this is giving us everything that it needs to give us. The creator of this map only wanted to get across to us whether or not a state overall voted blue or voted red, whether the win, essentially, of that state or the majority of that state leaned one direction or the other. However, if you wanted to make a map talking about the number of voters in each state, it's going to be a very different looking map. Now you're talking about population density. If you're looking at whether or not everyone in the red state voted Republican, now you need to look at a gradient. You need a color gradient to represent, kind of like, I'm going to bring us back here, kind of like this map at the bottom, whether there was a very strong leaning towards Republican or a very strong leaning towards Democrat or somewhere in between. So this is again another example of maps and their symbolization as well as their representation. And the question here is, which one of these is the truth? Now, each one of these maps is showing us something different, but they're all showing us data from the 2004 presidential election. You'll see that on the left, we have a pretty, what we would consider a normal looking map of the contiguous US. We have our reds and our blues. On the right at the top, we have a more distorted image where we can kind of tell that it's the US from what we know of it because we can tell what Texas looks like, but there's a distortion now happening with it with the same shading. Excuse me. And at the bottom, we have again what looks like a typical contiguous United States representation, but now we have a lot of shading that's happening, a lot of purples and reds and blues. So which one of these is the truth is the question here. And really the answer is that each one is trying to show you something different. Typically, I would play this video for you all if we were in a synchronous course, but I will let you all look at this, type it into your browser. I highly recommend and request that you watch this because not only is it a very good video, but it really gets across why each one of these maps exists and how each one of them is in the real world utilized to get across different information, essentially. Essentially, what that last, I called it a video, but that article will show you is people can lie with maps, and people often will lie with maps. So pay very close attention to your data and pay very close attention to how you are representing your data. Everything on here is the same data displayed in a different way. And because of that, each one of these maps, as well as the maps on the slide before, give the viewer a very different idea of what is going on, even if all the data is the same. So maps for you to think about will be maps of population sizes in states, maps of crime locations across cities, tourist maps when it comes to you going to a new place. Where are the fishing holes? Where are the swimming holes? Where are the concessions? And where are roller coasters if you're going to somewhere like that? If you're going hiking, where are you in terms of a restroom or a common meeting point? Where is the elevation increase, you know? You also want to think about maps for printed books versus figures in a book versus presentations versus interactive maps. The point here, and kind of to close this portion out, is every map that you make is going to have a very specific purpose, and what that purpose is leads you to how to create it. You do not create a map before you know what the purpose of that map is. If you want to show somebody the difference in voter registration across counties, you're going to symbolize that very differently than if you want to show somebody the difference in elevation across counties. If you want to show somebody the interstate highway system, it's going to be a very different type of map than the water bodies of Virginia. These may sound, again, very inherent and intrinsic things that you would understand, but the reality is you have to think of these things now that you are on the other end of the map making before you create those maps. So with that, your lab overview essentially this is talking about what your tutorials and your assignments will look like. This section, chapter 2, really focuses on your symbols, attribute tables, your projections, and your distortions. So as you work through tutorials as well as your assignment for chapter 2, these will be the topics that essentially you are focusing on the most and that you are trying to learn from. I emphasize this to say, as you go through your tutorials, before you even get over to your assignment, if any of this is unclear to you, please make sure that you pay close attention to your tutorial workbook and you go back through these slides, as well as use Piazza if you have questions. So with that, that is the end of lecture 2. If you have any questions, please post them on Piazza. Remember to post questions and answers to questions on Piazza as you go. Utilize your slides and your videos, and utilize one another through Piazza again to figure out things that you might get a little hung up on. And as always, if there's anything that you do need from me directly, please do feel free to reach out via email if you've gone through your other resources. So with that, this is the end of lecture 2. You're going to be moving on to lecture 3 next.